Hey, welcome to the 11th class meeting of EECE341, Introduction to Communication Systems. The first and most important announcement is about the midterm. And as I announced last time, it's highly likely that we may take the midterm on Wednesday, October 23rd. From 7 p.m. to 10 p.m. In this classroom. I'm also planning to take it on 21st if you have any conflict. So please let me know. So if you have any mandatory courses for freshmen and sophomore, those classes on this day, and if you are taking that course, then probably I have to move it to October 21st, Monday. The time would be the same, and the coverage may be reduced. But as always, and as in the quiz, it's an open everything exam, except no communication with human. Got it? Homework 10 and 11 and 12 will be assigned as usual. Okay, so here goes the big picture. I hope we can finish at least chapter 3 before the midterm exam. As I told you, this chapter is the most important chapter in this course. And also, this must provide you a solid foundation to study any communications, including digital communications, that is offered next semester. So this chapter 3 is the foundation. So study very hard. And you will be not only rewarded in this course, but also rewarded in the digital communications course too. Then we will move to angle modulation and the other topics. Okay, here goes the review of the last class meeting. What was most important was the double sideband modulation. So I draw a Venn diagram. Let's say that this is the set of all modulation schemes or modulation method. Then we can just simply divide it into two, and the left side is called linear modulation schemes, and the right side may be called nonlinear modulation schemes. Of course, this dissection depends on the definition. Okay, if we remove a affine transform from linear transform, because precisely speaking, affine transform or affine mapping is not linear mapping, then we may put double sideband modulation in the nonlinear modulation. But anyway, the convention is that the double sideband with the transmitted carrier is also classified as linear. So here goes a set of DSB modulation schemes. Got it? So we have focused on this one. We have been focusing on this one. And today we are going to expand our modulation scheme to something like single sideband modulation and vestigial sideband modulations. Got it? Of course, this may be very, very small, thinking about every possible linear modulation schemes. But anyway, you can draw any Venn diagram. Okay? And in DSB, we can divide it into two. DSB with suppressed carrier, which means no additional carrier signal, no unmodulated carrier signal. And here is DSB with carrier, or some people say DSB with transmitted carrier. And within this DSP with carrier, there is something called DSP with large carrier. This L means large usually. And alias, a nickname for this is AM, unfortunately. Got it? So mostly if a modulation scheme is referred to as AM, that does not mean modulation scheme that modulates amplitude. That rather means DSP LC. Be careful. Most of the people, when they say amplitude modulation, they mean DSP with large carrier. And this large adjective is always, how to say that, not absolute, relative. So we had a precise definition for this one by introducing the concept of modulation index. And what was our approach? First, we assumed we have a real valued baseband message signal. So this is real valued and baseband. And of course, this M of t may be, mathematically speaking, any real valued baseband signal, but sometimes, be careful, sometimes it has a symmetry, but that symmetry is not precise mathematical symmetry. For example, if we have a symmetrical signal, what does that mean? If the signal is viewed as a function of t, then it evaluated at t0 equals it evaluated at negative t0 for all t. That is kind of symmetry. If we put negative sign, then we have odd symmetry, positive sign, even symmetry. If you put conjugation, then conjugate symmetry or Hermitian symmetry, something like that. The problem is that M of t symmetrical with respect to time axis. Actually, this is not precise definition. Means that if you have some part of M of t that is above the time axis, then you have something very similar to that. Got it? That's what this symmetrical with respect to time axis means. It's not like if this signal is viewed or inverse function is viewed as a function of y, then you have inverse function of y0 equals the inverse function of negative y. It does not mean that. Got it? So this symmetrical is very vague definition. The reason why we assume this something strange, which is not that mathematical, is because this is one of the very important property of a voice or speech signal. So suppose this is a voice signal, then you will see something like that. What does that mean? If you have some positive peak value, for example, A, then you have highly likely that you have negative A, something like that. It may be because we use microphone that is a kind of membrane vibrating depending on the pressure applied to this membrane. And we have some zero offset. So this membrane goes up and down and up and down. And due to the kind of elasticity, then this membrane goes back to the original position, right? And also in the microphone, usually we remove DC, any direct current component. So that's why we may have this interesting property. Anyway, what we do is that we normalize or we scale or normalize block that is very conceptual, okay? The practical or real world AM modulator may not have it, but it's very conceptual. And what does it do? It divides the input with its absolute value of minimum of m of t. This is very strange, assuming that minimum value is non-zero. Okay? Then what is the name of the output? M sub n, and this n may be indicating that this is a kind of normalized version. And then what do we do? What we do is that we multiply some constant a, and we add 1, probably relative to that one, and then we do modulation. Okay, so here goes some AC cosine 2 pi fct plus theta of possibly t, very slowly varying. And to make everything simple, let's assume we have power amp and antenna to convert this electrical signal to a radio wave. Of course, from here, the signal is already an radio wave that propagates through the RF cable, but we model this one also as an electrical signal that is a function of time. That's what I said. Right? So in reality, if this cable is replaced by a longer one, you may have different phase applied to power amp. I emphasize and never forget this one. This may appear on your exam. Got it? So be careful. Anyway, so our transmitted signal for DSB large carrier will look like this. Got it? So this is the transmitted signal. Of course, transmitted signal is a radio wave. So this is a kind of simplified abstraction. Got it? We'd rather say that this is the signal applied to the antenna. Got it? Of course, the applied to the antenna is the signal is a wave, not this continuous time signal. But anyway, now this is the TX part. And of course, we must think about channel, but to make everything simple, we assume the channel is a very simple some delay line or something. So we have some attenuation or gain factor here. Probably I use the capital G. It doesn't matter, but anyway. And we have some delay. This is a very typical in a free space, right? Even though you have a radio wave propagating through the channel, at the receiver, we again will convert the radio wave to a radio frequency signal. So at this point, at the output of low noise amplifier, our signal may be well modeled as something like this. Okay, so scaled and delayed version of the transmitted signal. It may be. Of course, sometimes there are noise. Sometimes there are interference components. But let's make everything simple. As I emphasized here, every time, the most important trick is to simplify, keeping the essence of the problem, right? So you remove what is not that important in the beginning. And then after you have an experience with the simplest or simplified version of your problem or task, then you add the complexities back. That is the key, right? by doing that, you may solve any problem that can be solvable. Okay? Probably you remember from your experience in high school, especially in solving math problems, sometimes at the first glance, some formidable looking problem turns out to be, after 10 minutes, 1 hour, very trivial and obvious, right? You have that experience. Same thing actually happens again and again in the undergraduate program, graduate program, even in your future graduate research. The most often frequent mistake made by us is to give up without simplifying and tackling the simplified problem. So never forget, simplify, tackle, get the experience, have the lessons, and go back to the original problem. Anyway, so let's assume that the received signal is simply a scaled delayed version, or even simply received signal is same as the transmitted signal. One of the reasons why we assume this one is that scale can be rescaled, scaling factor may be modified, and also this tau delay may have different reference in the transmitter and receiver. We never know the transmitter and receiver has the same time reference, time 0, right? So anyway, let's just simply take that tau out. Then what is the receiver that extracts m sub n of t, or equivalently m of t? The simplest is hinted by the trigonometric identity, that is this one. So what we do is that we multiply so-called the demodulation carrier that has exactly same signal as this factor. So cosine 2 pi fct plus phi of t, if it's possible. And then we remove the high frequency, twice the carrier frequency component. Then we have what? We have this part scaled. And you have, for example, DC block. Then you have something that is proportional to the message signal. When A is between 0 and 1. And I emphasized why this is true. So just a second. No, this is always true. Sorry, I got confused. So if this coherent, I'm very sorry, if this is coherent demodulator. So in this coherence demodulation, you don't need this condition yet. Got it? So this is coherent demodulator. And we had the envelope detector. So this is coherent, or sometimes phase-coherent demodulator. And here goes the envelope detector. An envelope detector is especially devised for AM, actually. What you do is that instead of finding and generating exact demodulation carrier that is the same as this factor, what you do is that you do your just best that has very close carrier component, so that every other phase noise can be put into other time varying function, theta of t. And then here goes the envelope detector. Then you have what? You have the envelope of this signal. And in order to understand what is the output here, you need to convert the signal to the envelope detector. Sorry, I'm sorry, something's wrong. Okay. It seems I prepared too much for today's lecture. In today's lecture, we have a heterodyne receiver. So let me focus. I'm sorry, let me forget about this. Okay. Not yet. So here goes the envelope detector. And let's take a look at this signal again. So we assumed this is y over t. And what is this one? As a real part of something. And this is too obvious because cosine is e to the j something. So you have AC 1 plus a mn of t. And you have e to the j 2 pi fct plus p of t. An envelope detector takes the envelope of the signal and outputs its absolute value or modulus. So here, what you have is AC, mathematically speaking, a mn of t. And here goes DC block. And what you want is here something proportional to m of t. One of the sufficient condition is A is between 0 and 1. Ready? Otherwise, you have distortion at the output. That is shown here. Let's see this one. Okay. So this is one of the most important figure in understanding the modulation index of AM. So if A is between 0 and 1, you can extract the envelope without distortion that contains the message information, message signal. But if A goes over 1, the unity, then you have something wrong because this is the envelope of the signal. Ready? So never forget you have proper modulation index. Now, let's go back to the question why we devise the double sideband with large carrier. Because here in the coherent demodulation, it's not easy to have the exact phase coherence, which means that same phase angle at the local oscillator of the receiver and the received signal. So having this one same as that one is practically impossible, especially when you have very inexpensive receiver. It's not easy to generate a very stable sinusoidal signal with a very stable carrier frequency. You may have a lot of phase noise. And also, you may have carrier frequency offset. Okay? So it's like, if I make an analogy, you have a target, and you not only have wide spread, but also your mean value has offset. Got it? That is kind of, if you understand my analogy, then that is the carrier frequency offset. Not only the phase noise, carrier frequency offset. So having a coherent demodulator at the receiver may be very costly. Of course, this kind of receiver works not only for DSP large carrier, but also DSP suppressed carrier. And also you've seen that DSP with large carrier wastes some transmission power because it transmits DC component, unmodulated carrier. So it's a trade-off between receiver complexity and power efficiency. And people in the early stage of radio broadcasting, when they adopted amplitude modulation, DSP, they decided to adopt DSB with large carrier because it makes receiver very simple. How? By using envelope detector. And you may say that, wait a minute, envelope detector, mathematically speaking, it must be able to convert the real bandpass signal in real times some complex times e to the something, and that is a mathematical operation probably cannot be done by a freshman and sophomore electrical engineering student, right? Now you can do that. Then how can we build such a circuit or such a chip to compute some complex signal? And also, how can we build a circuit that takes this part only and compute the modulus of a complex value signal? It seems it's much more difficult to have a local oscillator that has phase coherence with the received signal. But as I told you, there are two buildings in electrical engineering. And on this right side of the building, people study what would be good if some mathematical operation or logical operation can be done using electrical system. Sometimes this is too theoretic and too advanced compared to the current implementation level. However, this left building electrical engineers are also very hardworking people, and they are very creative. So they devised a practical envelope detector that even is built by analog components, not digital components, right? For example, ask ChatGPT by giving this y of t and, hey, what is the envelope of this signal? And what is the complex envelope of signal? ChatGPT may give you a wrong answer, okay? The state-of-the-art LLM may still give you a wrong answer, but in 1930s, people already devised an analog circuit that does envelope detection. How? They used nonlinear devices such as diode. At that time, it was not a diode, but anyway, some circuit that performs mathematically same as the diode, and they use the resistor and capacitor to have this envelope detector. Of course, approximate, got it? And you will find from your textbook, probably you've seen already that I'm putting a lot of reading assignment in the homework because you never read the textbook. So, but anyway, if you read, usually the early radio communication engineers adjusted this product of R and C values in order to have appropriate RC time constant, so that, as you see here, the envelope of the signal can be, not exactly, but can be properly tracked by the envelope detector. Got it? Anyway, so one of the reasons why I emphasize a lot about this chapter is this one. Feel the history about the development of these radio communications. Okay? They had a lot of challenges. They even could not generate continuous wave, but they made it possible. They didn't know even how they can efficiently transmit a radio wave signal, but they overcome the difficulties. Sometimes even without having a solid theory, they were very hardworking, right? And sometimes there were good theories, mathematical theories, couldn't be realized at that time, but they made it possible. Got it? By doing a lot of creative thinking. Got it? So isn't it amazing? And actually, that is still the case at this time. For example, some algorithms to estimate the wireless channel that to improve the performance of your cell phone. Sometimes some researchers on the right side building, they say that, okay, we need to do singular value decomposition every nanosecond. Impossible, right? Even with state-of-the-art NVIDIA something, right? But what people do is that not only they have that kind of result, they do mathematical approximations to reduce the complexity, computational complexity. There are some very interesting algorithms that extract, for example, not every eigenvalue, but the strongest eigenvalue and eigenvector. There are some iterative algorithms. So given a square matrix, finding an eigenvector that corresponds to the largest eigenvalue can be iteratively obtained. So you just need to compute something like y equals ax iteratively with different axes. But so probably at this stage of your study, undergraduate study, probably you love something exact, right? Something closed formed. However, in reality, it's not because of the implementation complexity. So sometimes, even though you are living in the right side building, saying that, okay, we need an eigenvalue decomposition at every 1 nanosecond, but sometimes you'd better provide some good approximation algorithm so that these guys may implement that idea with slightly improved technology. Anyway, so let's go back. I'm talking too much. So amazingly, the early radio communication era, the engineers could build envelope detector so that this extra carrier, you see, this is the extra carrier part, really helps to build a cost-effective receiver. And that was the beginning of the radio broadcasting. Okay, so it seems that we have a good trade-off. There is trade-off. Yeah, we have a good trade-off between the power efficiency and the receiver complexity. So these are pros and cons of the AM, in other words, DSP large carrier. So we have reduced receiver complexity. However, we have little bit poor or extremely poor, 50% or sometimes just 33% power efficiency. By the way, when the textbook and most of the textbooks compute the power efficiency of AM modulation, this assumption of symmetrical with respect to time axis or something similar occurs. In that case, your trick is that you have max of m of t equals mean of m of t to be used in your derivation. And you can show that the highest power efficiency for a message signal that has this symmetry property is a square wave type thing. So two value with different polarity. And in that case, you have maximum transmission power efficiency just 50%. And if you have exact sinusoidal message signal, then even the power efficiency goes down to just 33%. You must be able to derive that, show that. As I emphasized, the midterm exam would be highly mathematical, like your signal gen systems exam, not like Introduction to Communication and Networks that talks a lot, but not much mathematics. Be careful. There will be a lot of equalities should be in your answer book. Now, before we move to single sideband modulation, let's see what could be other alternatives to DSP with large carrier. So here goes DSP with reduced carrier, which means that in terms of modulation index for AM, A is greater than 1. What does that mean? If you keep using envelope detector, then you have distortion. But still, as I told you, if you can build coherent demodulator, even for A greater than 1, still you can extract M of T without distortion or without much distortion. So if you want really a higher power efficiency with now increased receiver complexity, AM is not the only choice. You just use the modulation index A greater than 1 and increase the complexity of receiver by employing, for example, Costas phase locked loop or squaring device-based phase locked loop. In that case, even you can put A tends to infinity, which means that equivalently, even without transmitting unmodulated carrier. About the phase lock loops, we will be back after we finish angle modulation. Okay, so I believe we covered most of the parts. By the way, we haven't carefully studied this part. So what happens in coherent demodulator in the frequency domain? By the way, this question is actually already asked you in the signal gen systems, depending who taught you. But the idea is simple. To make everything simple, let's just assume that we have the received signal that is some A times M of T cosine 2 pi FCT without phase, without unmodulated carrier. Then what happens? What you do is that you multiply the same carrier called demodulation carrier, and you apply the low pass filter. And what is the corresponding frequency domain representation? So here, let's focus on this part first, focusing on Y of T first. So Y of F equals what? M of F minus FC plus M of F plus FC divided by 2. Why? Times A. Because cosine is what? E to the J 2 pi FCT plus e to the negative J 2 pi FCT divided by 2, which is a kind of Euler's identity written in the other way, right? So you have 1/2 here. And what is the Fourier transform of the pure complex sinusoidal signal? A direct delta function with first FC and with negative FC. And what is the multiplication in time in the frequency domain? Convolution. That's why you have this one. So the input to the low pass filter is simply what? Simply something like this. Now, not Y, sorry. And then, sorry, you multiply cosine. So what happens? I'm sorry. This is that one, right? And you multiply cosine again. So what you have is that this entire thing shifted again. So you have 4 over A over 4, right? And then this one left shifted by FC. So you have something like this. So you have A over 2, A over 4, negative 2FC. So if you apply low pass filter, then these double frequency terms disappears and you have the message. Got it? So this is what's going on in the frequency domain. Of course, this simple demonstration becomes complicated if you have some phase. But anyway, basically the idea is the same. Now, so are we happy with variety of DSP modulations? We have DSP with transmitted carrier. We have DSP with suppressed carrier. And among DSP with transmitted carrier, sometimes we have DSP with reduced carrier, but sometimes we have DSP with large carrier. Are we happy? The problem is this one. We assumed the message signal is what? Real valued baseband signal. And what happens? The transmitted signal is also real valued, but see this part carefully. Especially this one. When we think about a general real valued bandpass signal, what did we have? So recall that some signal X is real bandpass. What was the most important result? There exists some complex baseband signal that has the real part xi of t and the imaginary part xq of t. And there goes complex sinusoidal part. And here you have real part and imaginary part. So you had what? Xi of t cosine something, which is called the in-phase component of this x of t. And you have negative x of q of t sine this one. Ready? And that is called the quadrature or quadrature phase component of x of t. However, in this AM or DSB, you don't have this part. What does that mean? In the frequency domain. That is actually all due to conjugate symmetry over real valued message. So let's go back to the message Fourier transform. So M of t has Fourier transform capital M of f. Say you have this bell-shaped type thing. And the conjugate symmetry means that if you evaluate f0, then you have some value, complex, and you have what? That conjugate here at negative f0. And what does that mean by this, a kind of symmetry? If I tell you that M of t is real valued, and I only provide you M of f for f positive or non-negative, then can you find this negative frequency part? Yes, because of this conjugate symmetry, right? And now, what happens if you multiply cosine 2 pi fct to M of t? Here, let's say this is R and this is L, right and left. What happens? Here goes R and here goes L. Here goes R and here goes L, right? Because modulating a message signal, so real value signal and cosine, what happens? You right shift this M of f and left shift. So you have LR, 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 something like that. Now, this is the transmitted signal in DSP SC, suppressed carrier. And now let me ask you, do we really need to send this upper side component and okay, what's going on? Okay. And this lower sideband component. Do we really need to transmit all of them? Obviously, the message is not only transmitted in this lower sideband, but also transmitted in upper sideband. What if at the transmitter, we could remove either the upper sideband part or the lower sideband part. For example, at the transmitter, you have a very sharp low pass or band pass, you may call, filter that only passes the lower sideband part of this DSB-SC. Can you still recover the message signal using some possibly complicated receiver? And the answer is yes. And let's see why this is true. So suppose we can still use coherent demodulator. Then what happens? As you've seen here, y over t times cosine 2 pi fct, what happens? This thing is right shifted, which means that you have this one and that one. See that? L and R, right? Got it? Now you have negative translation. And what happens? This goes here, right? And that goes, sorry, am I correct? Yeah, that goes there, right? So if you apply ideal low-pass filter, again, you have what? This signal back. Do you understand what I mean? So suppose you have, in some way, filtered out the upper sideband part of the DSB-SC modulated signal at the transmitter and then sent. And somehow, suppose you could find exact phase angle of the received signal and could use phase-coherent demodulator. Theoretically, you can still retrieve the original message signal with possible some scaling, right? So what does this mean? Due to the conjugate symmetry or Hermitian symmetry, or just say some books say symmetry in the frequency domain, actually double sideband family of modulation schemes wasted half of the bandwidth. So here in the original DSB, this was the passband bandwidth, possibly purchased from the government, right? You know that the SKT, KT, and LGU plus had what? Had to compete in the auction opened by the Korean government when they wanted to provide you 4G and 5G services, right? Government, 과학기술정보통신부 announces that that frequency bands would be sold to the company. So you apply. And KT, SKT, LGU plus applies with intention to pay a lot of money. Now, do you really want to use this band W that corresponds to this one? So let me say this is B and W is 2B. Got it? So B is the bandwidth of the message signal, real valued baseband message signal. That is translated to 2B, that is W, in the real passband. By the way, you may say that, wait a minute. Here, not only W, but also this W is also used. You are right. However, in radio communication, it's Just if you purchase this band, you purchase that band in terms of complex sinusoidal signal. Got it? We just say that I purchased SKT, for example, purchased 5 gig to 5.1 gig from the government. That means you also purchased negative 5.1 gig to negative 5 gig hertz at the same time. Got it? So anyway, in the passband, DSB use 2 times the bandwidth of the real baseband message signal. But it turns out that that is not necessary to transmit the information. So in this sense, here goes the, there is, yeah, here goes the key point. DSB was not efficient in the frequency domain. In other words, spectral, which means that frequency, okay? So this spectral efficiency means that frequency utilization efficiency of DSB was bad, okay? We could reduce it into half if we could build a very, very sharp filter that filters out, for example, upper sideband part. Actually, you can show that the same thing is true if you can filter out the lower sideband part. Again, if you have a phase-coherent receiver, you can recover the original message signal. Either you filter out upper sideband or lower sideband, which means DSB is indeed spectrally inefficient. Then, what would be the next step as an engineer? Probably you will think about having a new modulation scheme that has twice spectrally efficient than DSB. And you may say that, okay, twice, that's not a big deal. I can eat one set of McDonald's or 2 sets of McDonald's. What's the problem? As I told you, this frequency band is very, very expensive. And even from the beginning of the radio communication, that was one of the cause of national conflicts between nations, especially neighboring nations, because this radio wave propagates over a lot of coverage. So if I have a transmitter in my nation, the radio wave spills over the boundary. And imagine the era just before World War I. These empires were very, very greedy and always ready to have a conflict with other nations. So from the beginning of the radio communication, nations sent their representatives and had a kind of congress or meeting to reconcile these conflicts. Now, radio frequency is very, very important resource for radio communication. If you can reduce it into half, you may save $1 trillion for example, 6G communications. So same performance, but half the bandwidth. Maybe an amazing breakthrough or even disruptive technology at that time. Got it? So here goes the idea. Let's remove one of the sidebands. That is the idea of, where it is, single sideband modulation. And we are going to see that one. So single sideband modulation, the starting point is the double sideband modulation. You want to remove either upper sidebands or lower sidebands. And what would be the simplest approach to build that system? Sideband filter, okay? If it's possible. So this electrical engineers on the right side building may say that, hey, build a filter that filters out upper side or lower side. Then we are done. They may simply say that. And the question is it really simple to build such a filter? Like, okay, here goes the filter response. Something like that. Okay? What does this mean? You need to have a very, very sharp cutoff at the carrier frequency. And is it possible? And was it possible in the early stage of radio communication? As you learned in circuits theory, it's not easy, okay? Especially if the carrier frequency goes higher. You may need a lot of components to have very sharp cut, sharp transition interval in the frequency. And also, sometimes you have to change the carrier frequency. In that case, you have to change what? The filter's cutoff frequency depending on your carrier. Which means it's not easy, okay? So theoretically, only theoretically, sideband filtering is a solution to generate a single sideband signal that saves half of the transmission bandwidth. So after the kind of conception of this single sideband idea, the problem becomes a kind of trade-off research now. So how can we cost effectively implement single sideband transmitter? Right? So what would be the solution? Here goes the idea of Hilbert transform. And it's not, Hilbert transform is not a level of Fourier transform. Okay? Even though Hilbert is also a very fine mathematician, this Hilbert transform is a very special linear time invariant filtering. Okay? So let me use M. Suppose you have a signal M of t and an LTI filter, linear time invariant system, having impulse response h of t. Then what is the output? M of t convert with h of t. Here goes the definition. This LTI system, or this mapper or transformer. Here, transformer means that it admits a continuous time signal and generates another signal. This transformer with impulse response 1 over pi t is called, let me say, this filter, this system, this LTI system. The Hilbert transformer. Got it? That's why this Hilbert transform is not that level of Fourier transform, in the sense that Fourier transform is very general transformation, and Hilbert transform is a very specific LTI system. Now, this is defined in the time domain, and let's denote the output as m hat when the message signal is m of t. Got it? So the output will be denoted by m hat from now on. Got it? For y. Okay? M is the input to the Hilbert transform. M hat is the output from the Hilbert transform. Now, let me ask you a question. When message signal is a real valued, is the output real valued? And your answer is yes, because the impulse response is real valued, even though this is a strange function, right? Let me draw the impulse response of the Hilbert transformer. What is it? It's something strange, right? This is 1 over pi t in the time domain. And you can immediately see that this is not causal. And as you learned in signal-gen systems, if you want to implement a non-causal filter, what do? Theoretically speaking, you can't implement it. However, there is a trick. You introduce a delay. So instead of using this h of t, you delay the impulse response, which means that you have something like that, right? And then you approximate, assuming this tail is small enough. So, for example, you have something like this. Of course, still this part may cause you a headache, but anyway, by giving extra delay, by introducing extra delay, we may approximately implement Hilbert transformer, right? So let's assume that Hilbert transformer can be implemented with some delay and approximation. Now, what's good with this one? And as a Pavlov's doodling dog, 파블로프의 침 흘리는 개, you have the automatic response. Okay, what is the Fourier transform of this Hilbert transformer's impulse response? Which means that what is the transfer function? Of course, sometimes transfer function means Laplace transform, but here transfer function means Fourier transform of the Hilbert transform. What it is. And it's very tricky, but you can find from the table of Fourier transform, it's something like this. Negative j for f positive, j for f negative. And if you define the Fourier transform precisely as a Fourier Plancherel transform, you can show that here you have. But this is not that important. But anyway, so this is the Fourier transform. And it's not easy to understand. So what we do is that we visualize by simply drawing the Hilbert transform's transfer function. The problem is that the value is either negative j, which is pure imaginary, and j. So what we usually do is something like this. This is not true, but usually we draw it this way. It's obviously not true, but for simplicity, we draw it this way. So Hilbert transformer or Hilbert transform over signal does something very interesting in the frequency domain. In the time domain, it looks very complicated. You have an impulse response, something like this. What's going on? But in the frequency domain, it's much clearer because Hilbert transformer output, so m head of f, is simply this h of f times the message signal's Fourier transform. And suppose message signal is real valued. What will happen? We had the conjugate symmetry here, right? M of f is conjugate symmetry. And you can also show that this has conjugate symmetry. Why? Because m head of t is simply m of t convolved with 1 over pi t, which is real. Real value signal convolved with real impulse response is real, and this is also it has conjugate symmetry. But here goes something interesting. Think about this one. M of f plus j times m head of f. And let's write down By the way, for this one, many people write it this way. The Hilbert transfer function is 1 over j times sine or signum of f. Here, signum or sine of f gives you either unity or negative unity, depending on the sign of this argument. If f is positive, this is 1. F is negative, this is negative 1. And depending on your definition, sometimes f is 0, then you have 0. But some people love when f is 0, it's still 1. But anyway, so what happens? Here, we have j times, what is this one? That one. 1 over j, signum of f, and m of f. So you can factor m of f out, and then what do you have? 1 plus signum of f. What is this one? Again, let's visualize. This is either negative 1 or 1, and you add 1. So you have 0 and 2, right? Hey, it's interesting. So let's think about this divided by 2. Then what happens? What happens? The output is simply the positive sideband of message signal. So m of f plus j m head of f divided by 2 is what? This positive side part. Some people say upper, but anyway, here, only this one. And I said this is what? This is the analytical part, analytic signal part of m of t, right? For f negative, no signal. This is interesting. So what does that mean? If you take the inverse transform, you have m of t plus j times m head of t. Gives you what? A complex value signal. Why? This is real, m of t is real, m head of t is real, but you have j. So this is a complex baseband signal, right? That has Fourier transform, this one. And since we are running out of time, let me just tell you. Using the Hilbert transformer, you can implement upper sideband, single sideband modulation, or lower sideband, single side modulation. And let me show you the diagram first. Here, it's very confusing, so temporarily forget, sorry, not this one. Forget about this part, right? Okay, so this is the block diagram of the transmitter, so TX. So this is the block diagram for the upper sideband tuned SSB, or upper sideband transmitting, single sideband transmit modulator. So here it also use the slash, but anyway. And let's see what's going on. Here you have the message, right? As the input to this SSB modulator. And here goes the message. And here goes what? What is this one? This is simple Hilbert transformer. Got it? Of course, for the implementation, you need some delay and the same delay here. But for mathematical simplicity, we just didn't consider that. So this is m of t. And this is what? M head of t. And you may say that, Professor, we needed j something, but actually, what we do is that here is our local oscillator that generates the carrier signal. This is, you can say that this is LO at transmitter, local oscillator at transmitter. It also said carrier oscillator. And this oscillator generates cosine 2 pi fct plus theta and sine 2 pi fct plus theta. And what you do is that you multiply. You have a mixer that mixes this cosine carrier with original message, and you have another mixer that multiplies sine carrier with the Hilbert transform of the message. Now, what you do is that you subtract the lower branch output. And what is this one? What is this one? This signal is m of t cosine, let me use 2 pi fct plus theta, because this is too simple, and minus m head of t sine 2 pi fct plus theta. And now, as a student who took my course, taking my course, you must be able to convert this one immediately in this form. Got it? So, what is this one? This is the positive sideband of message, right? Or upper sideband part of the message. If we put 1/2, so let me put 1/2 somewhere. Okay, here is 1/2. So let me just move the point. So here you have half AC and half AC and AC, and you have half. Got it? And now let's try to rewrite this real part again. So you have AC and half m of t j m head of t e to the j 2 pi fct plus theta plus AC 1/2 m of t negative j m head of t e to the negative j 2 pi fct plus theta divided by 2. What am I doing? I'm replacing this real part operator with what? 1/2 the argument plus its conjugate, right? So here, real of z equals z plus z conjugate divided by 2. I used it. Got it? So this one appears here, and its conjugate appears there, and you have divided by 2, right? You must be very dexterous with this trick if you want to study radio communication. Given a real valued bandpass signal, you can instantly be able to find out its complex exponential version, and also this complex signal representation. This is complex signal, that is complex signal. But let's view it in the frequency domain. What is the first term? See that this is the upper sideband part of the message. What happens if you multiply e to the j2 pi fc? It moves right side to fc. Now, what happens for this one? This one is what? This one is the upper side, the upper term. It's conjugate version. And if you put conjugation in the time domain, in the frequency domain, it becomes conjugation and negation of the signal. So what you have is what? This becomes, so this one becomes that, and that one becomes this one. That's why you have upper sideband tuned single sideband signal. Got it? And you can do the same thing for the lower branch. At the output of a lower branch, you will have single sideband signal that has lower sideband tuned. Got it? So that is the idea. So without using the formidable complexity sideband filter, you may utilize Hilbert transformer if it can be well approximated and implemented using a circuit at your age. Got it? Okay, that's all for today.